Welcome to The Explainer. Today, we're going to demystify something that sounds super intimidating, stoichiometry. But here's the secret. If you can follow a recipe to bake cookies, you can totally get this. By the end of this, you'll see that calculating a chemical reaction is pretty much the same thing. So here's what we've got on the menu today. We'll kick things off with that recipe idea, get to know the chemist's version of a dozen, figure out how to read the instructions, and then walk through the actual math. And finally, we'll even connect it all to the snacks in your lunchbox. Okay, so first things first, let's just think of chemistry as like super precise cooking. Seriously, it's all about knowing exactly how much of your ingredients, we call those reactants, you need to make your final dish, or what we call the products. Think about it. If you want to bake cookies, you need a recipe, right? Well, what's the recipe for a chemical reaction? It seems like a simple question, but honestly, the answer is the key to pretty much everything we're going to talk about. You can't just toss chemicals together and hope for the best. You need a guide. And here it is. This is our recipe in chemistry, the balanced chemical equation. It's basically the master recipe card. You've got your reactants, the ingredients, on the left, and your products, the final dish, on the right. That little arrow in the middle, that's the magic, the transformation from one to the other. And you know what? Every single chemical recipe has to follow one single unbreakable rule. It's a big one, the law of conservation of mass. All it means is that you can't create or destroy matter. So the number of atoms you start with has to be the same as the number of atoms you end with. They just get rearranged. That's why we absolutely have to balance the equation. Okay, so we've got a recipe card, but how do we measure the ingredients? I mean, we can't exactly use cups or tablespoons for atoms, right? Chemists needed a way to count things that are just, well, they're unimaginably small. Right, a recipe might call for cups or grams, but in chemistry, the master unit for counting atoms and molecules is the mole. Since trying to count individual atoms is, completely impossible, chemists group them into this one handy unit. It's kind of like how we use a dozen for eggs. For atoms, we use a mole. It's the unit for chemical amounts. So just how many things are in one mole? Okay, brace yourself. It's 6.022 times 10 to the 23rd. That is a 6 with 23 zeros after it. It's a ridiculously huge number, which, when you think about it, just shows you how incredibly tiny atoms and molecules really are. And this beautiful thing is the mole map. Think of it as your cheat sheet for chemistry math. And look, notice what's right there in the middle, connecting everything? The mole. It's the central hub. It lets us convert from the mass of something to the number of particles in it, or from the volume of a gas back to moles. It is the ultimate translator for a chemist. All right, we've got our unit of measurement down, the mole. Now it's time to learn how to read the most important part of our chemical recipe. I'm talking about the ratios. So, what is the mole ratio? Well, it's just the ratio of moles of one thing to the moles of another thing in a balanced equation. That's it. Think of it as the bridge that lets you go from one ingredient to another, or from an ingredient to the final product. It's the key that unlocks pretty much all these calculations. And where do you find these ratios? Easy. You just look at the big numbers in front of each chemical. We call those coefficients. So for making water, the equation is 2H2 plus O2 gives you 2H2O. The coefficients tell us the recipe is super specific. You need exactly 2 moles of hydrogen for every 1 mole of oxygen. Okay, let's put it all together. We have the recipe, we can read the ratios. Now it's time for the main event. Let's actually walk through the steps and do some calculations. This right here, this is the classic mass-to-mass path. It's the backbone of pretty much any stoichiometry problem you'll see. It's always the same 3 steps. 1, you convert the mass you're given into moles. 2, you use that magic mole ratio from the balanced equation to find the moles of what you're looking for. And 3, you convert those moles back into mass. That's the path. Okay, practice time. Let's try an example. How many molecules of CO2 are in 3.5 liters of CO2 gas? Now, this one's a little different. It goes from volume to particles, but the idea is exactly the same. We're going to use our conversion factors, and the mole is still going to be our bridge. What you're seeing here is a technique called dimensional analysis, and honestly, it's brilliant. We start with what we know, 3.5 liters. Then we multiply by a conversion factor to change the liters into moles. See how the liters unit on top cancels out the one on the bottom? Perfect. Next, we use Avogadro's number to go from moles to molecules. And again, moles cancels out. All we're left with is the unit we wanted all along, molecules. It's like the units guide you straight to the answer. Now, you might be thinking, okay, cool, but when am I ever going to use this? Well, this isn't just some abstract thing for your chemistry class. Stoichiometry is everywhere. I mean, it's used to make life-saving drugs with super precise dosages. It's used to engineer the batteries in your phone. It's all about getting the recipe right. We can even find it in your lunchbox. So let's get real. How many atoms of sodium are in a bag of chips? Sounds like a crazy question, right? But believe it or not, that little nutrition label on the back gives you everything you need to figure it out. And guess what? It's the exact same path we just talked about. First, you look at the nutrition label and find the mass of sodium chloride, which is just table salt. Then, you convert that mass to moles. You use the mole ratio, which is a simple 1-to-1 for this. And finally, you use Avogadro's number, that giant number, to find the actual number of sodium atoms. Wild, right? And it's not just for salt. You can do the exact same thing to figure out how many molecules of sugar are in a can of soda. Food scientists do this all the time to make sure every single can tastes the same. Just find the grams of sugar on the label, convert to moles, then convert to molecules. See? It's stoichiometry in the wild. Okay, so up until now, we've been living in a perfect world where every recipe works out perfectly. But let's be real. When you bake, do you get every last bit of batter out of the bowl? Probably not. Well, chemical reactions in the real world, they're not always perfect either. And this brings us to two really important ideas: theoretical yield versus actual yield. The theoretical yield is what you calculate on paper. It's the absolute maximum amount of product you could possibly make if everything went perfectly. But the actual yield, that's what you actually get when you run the experiment in the lab. And spoiler alert, they are almost never the same. So why aren't they the same? Well, lots of reasons. Maybe your starting ingredients weren't totally pure. Maybe the reaction just didn't finish all the way. Or sometimes other pesky side reactions happen that use up your ingredients to make something you didn't even want. Yeah, reality can be a bit messy. So here's the big takeaway. The next time you see a balanced chemical equation, remember, that's just the ideal recipe. It's the blueprint. But in the real world, other things, variables like temperature or pressure, or even just how you mix things, can totally change the final dish. The recipe is where you start, but mastering those variables, that's where the real chemistry begins.